Can see that. Oh, right. Bring my notes back. Okay, so the Megaconstellation Threat. So I want to talk about the Megaconstellation Threat. First of all, what are megaconstellations? And I'm going to talk about the various reasons why they are a threat to astronomy, but more than just a threat to astronomy, but a threat to the use of space, the safe and sustainable use of space. And I think also potentially megaconstellations could be one of the triggering forces that will lead to international tensions later on. Space is becoming a new domain of human activity, and as always, when you get a new area that becomes available, be it an area of commerce or a new piece of land or a stretch of sea or something like that, people will start to be in contention for it, and a bit of a land grab, or in this case a space grab, is going on, and that could raise international tensions, and I'll talk about that towards the end. So first of all, satellites. First satellite launched, Sputnik 1, 4th of October 1957, so that's quite a few years ago, 64 years ago. There have been over 11,500 satellites launched since then, of which currently there are more than 4,500 still active. Now, in the early days, satellites were big things. They were put up there for military surveillance, but mostly for communications. And the satellites were big. They were the sort of thing that only companies could afford, or nations could afford. You were talking about 6,000 to 8,000 kilograms, big things, and hundreds of millions of dollars, not only in terms of the cost of making the satellite, but also the cost of getting them launched. And on top of that, you've then got the tracking stations and all of the infrastructure that goes behind that to keep the satellites running and have the data that's coming down relayed to where it needs to go. Over time, of course, electronics has got smaller. It's gotten smaller because you've improved miniaturization. It's gotten smaller because you've managed to, you wanted to bring the power consumption down, and the smaller you make them, the less power they tend to consume, and the faster they get. So because you can make the electronics smaller, and we've got all this experience making satellites, they're now much smaller, and you can get a satellite now into orbit, usually piggybacked on a launcher along with other satellites, for between $25,000 and $250,000, depending upon what kind of small satellite you might want to launch. So whereas back in the early days, you had the big communication satellites up there, and they were responsible for beaming your radio signals, or television signals, or telephone signals around the world. Now you can bring your satellites lower down, and you can have thousands of them. And the cost, it may even be lower than putting up one very large satellite. So first of all, to talk a little bit about the kind of orbits that you have. So first of all, this is these numbers come from the Union of Concerned Scientists, and accurate up to beginning of September this year. So we've got elliptical orbits that cover a range of altitudes, and there are about 57 satellites that come into that sort of category. One of the quite common forms of elliptical orbit is known as a Molniya orbit, which is shown here over on the right-hand side. You can see a satellite that's in a highly elliptic orbit, and it's designed so that if you look here at the 1 hour intervals here, it has a 12-hour period, which means that it goes around the Earth twice in one Earth rotation. But also it's inclined at 63 degrees, which means that the torque caused by the bulge in the Earth's equator causes the orbit to precess around the Earth's axis, so that over the course of a year, the orbit always faces, if you like, towards the sun. So it keeps it as a very predictable, stable orbit. Now, the advantage of these orbits here is that you can see, as with all orbits, when you get to a periapsis, or in the case of the Earth, perigee, then here, excuse me, the gap between 0 hour and 1 hour is quite a long distance around the orbit, similarly 11 hours to 0 hours. However, when you get up to the far end, to apopsis or apogee, you can see here that the distance traveled in 1 hour is much shorter. So this means that the satellite whips around the Earth at the bottom here and then sort of lingers around the top up here, looking down at latitudes of about 63 degrees above and below a bit, and able to spend quite a lot of time looking at some continent of interest. So it's not surprising that the Molniya orbits are the ones that are very popular with the surveillance satellites, the military surveillance satellites in particular. You've then got the geosynchronous orbits. Now, geosynchronous fall into two categories, really. Geosynchronous, all that means is that the satellite has a 24-hour period, and therefore it goes around the Earth's axis in the same time as the Earth rotates. So that if the orbit is circular and it is coplanar with the Earth's equator, so equatorial orbit, then it means that the satellite will stay above the same point on the Earth's surface for the whole time. So that's a special class of geosynchronous orbit known as a geostationary orbit. It has the big advantage that if you have a satellite dish on the side of your house, such as you use for Sky TV or something like that, the satellite stays at a fixed point in the sky. And so you don't have to steer your dishes, which obviously has the big advantage that they can be cheaper. If the satellite's orbit is inclined, then as the satellite goes up and down as it goes around the Earth, then the satellite will move above and below the equator. And if the orbit is slightly elliptical, then it will show a figure of 8 as it goes up and down above that same average longitude. So again, very useful, and the amount of tracking you need to do is reduced if you've got a geosynchronous but not geostationary satellite. But they're a long way out, 35,786 kilometers altitude. So when I'm talking about altitude here, I'm not talking about distance from the center of the Earth. I'm talking about the distance above the mean Earth's surface. And there are currently about 564 satellites in geosynchronous or geostationary orbits. Then we have the medium Earth orbits, not so common these, because these are satellites that are orbiting faster than 24 hours, but slower than the low Earth orbits of 90 minutes or so. So there are some uses for that. They tend to be slightly elliptical for special purposes. So you're talking here for a medium Earth orbit as being about 2,000 kilometers up to the geosynchronous orbit altitude. Then you've got the low Earth orbits or near Earth orbits. This is a couple of thousand kilometers down to, well, typically 250 kilometers just about. Much lower than 250 kilometers, and your satellite doesn't stay in orbit for very long because of drag from the Earth's atmosphere. The term LEO or NEO, I much prefer LEO because NEO is also sometimes used for objects in a heliocentric orbit that are orbiting on paths that bring them close to Earth, which is not quite the same thing here. We're talking about low Earth orbit, which is satellites orbiting around the Earth in a very low orbit of 500 kilometers or something like that. One very common configuration here is this here, the Walker configuration. And you can see here, this is actually a series of orbits. So here, this is one orbital plane, and this is another orbital plane, and this is another orbital plane. And so they're all of the same inclination. They all have the same spacing, if you like, in terms of distance where they cross the equator. So you form this kind of basket weave of orbits. You may actually have several satellites, and it's quite common to have several satellites in the same orbital plane. So you may, for example, have 24 satellites going along one of these orbits, and another 24 going along one of these, and another 24 along one of these. Carefully spaced out so that they don't collide, maybe with small variations in altitude or something like that, but generally all much of a muchness in terms of altitude. So this is the Walker configuration, and in fact this is the kind of orbit that will be mostly the subject of tonight's talk. So it says here altitude is less than 2,000 kilometers, but really most of the satellites that are being used, and again going to be part of the talk tonight, are about 1,000 kilometers or less, down to, in some cases, 290. So what are the mega constellations being proposed so far? Well, you're not surprised perhaps to see SpaceX's Starlink satellites there at the top. Some of the grey ones are definitely under proposal. One or two of the black ones are also under proposal. They haven't, as in their plan, but they haven't been built yet. So we have, for example, SpaceX. SpaceX have already got permission to launch nearly 12,000 satellites into orbit, of which they've already got nearly 2,000 into orbit. Mostly these are going to be at altitudes of 515 to 580 kilometers. They have applied for an additional 30,000, which is the ones here in grey, bringing their total planned system up to 42,000. That's if they get permission to launch the other 30,000. Amazon have already got approval to launch these here, and these are also in proposal but haven't been given permission for yet. And you can see that there is similar sort of altitude, 650 down to 590. The Chinese have a constellation here that they're planning, again similar altitudes. But you can see that some people are bucking the trend slightly. There's Samsung here at 2,000, Boeing at 1,030, and then you've got companies like OneWeb here down, which is the UK and Indian company, Indian Bharti International is the company, a consortium, planning to launch them up to 1,200 kilometers. Now, if we add up all the ones that are in black, then you come to 70,289 satellites. As I say, some of these here may be grey, so this number maybe is slightly lower. However, this doesn't stop other companies putting in plans to launch satellites, and maybe some of these will get approval. I wouldn't be surprised if Amazon get approval for their few extra ones. Of course, people like the Chinese don't need permission from the FCC or Ofcom to launch their satellites. They're just going to go and do it. And then most recently, there was a rather interesting one, an addition by the Rwanda Space Agency, who, as far as I'm aware, don't have a space launch capability. And they've put in a proposal for 327,320 satellites. I take it with a pinch of salt. I can't really see them mustering by themselves, mustering the launch capability or the funds to put that many satellites into orbit, let alone the infrastructure, etc., etc. It may be that they will have backing from another country, maybe the Russians, to do something like that. But we'll take that one with a pinch of salt. It's quite likely that by the time we get to within the next 10 or 15 years, there will be 100,000 active satellites in low Earth orbit. This is a significant increase on the number of active satellites currently in low Earth orbit. And it's this large number of satellites that is causing all the brouhaha from astronomers, from the space scientists, and so on. So, as I said, SpaceX had to get permission to launch their satellites. This is just SpaceX from the FCC. Now, the FCC is an American government agency, and they allocate frequencies that SpaceX are going to use to communicate with the satellite. But they act on behalf of the International Telecommunications Union, which is a United Nations organization. Now, the Ofcom are the same. Ofcom allocates frequencies for OneWeb on behalf of the ITU. Now, there are rules that if you reserve a set of frequencies that you're going to use, you can't just keep them open. You can't just sort of frequency squat until you've got your satellites launched. Otherwise, the bandwidth would very quickly, the band would very quickly get used up. And nobody could launch any satellites. You'd have to put some sort of limits on it. So SpaceX have been told that these phase 1 satellites here, this first batch, which is what they're launching at the moment, these have got to be half completed by the 29th of March 2024 and fully completed by 29th of March 2027. So you can see here this first line here of just over 1,500 satellites in 72 planes. So if you think back to my Walker configuration diagram, that basket mesh of orbits, that means there are 72 planes staggered around the Earth's equator altogether. And then at a slightly higher altitude, there's another 72 planes at a similar inclination. And then there are some polar ones or near polar ones. In fact, these are slightly retrograde, near polar ones. And then there are some others here at a high inclination. Now, given that mostly what Starlink are aiming for, SpaceX are aiming for with Starlink, is to provide communications, internet communications for North America and Europe, you can see here that that's why this 53-degree inclination is important. These higher polar ones are for some of the polar latitudes that are higher up, so places like Alaska, for example, they will get some coverage but not as good. And I'm not quite sure what the 70-degree ones are. Some of these may be put up there on behalf of the military, because certainly part of the Starlink network will be used by the military, perhaps a dedicated part. Not just certain channels, if you like, being allocated to the military. So there's phase 2 here. Now you notice that these are going to be launched into lower orbits. So there's going to be more work required to keep those satellites in position, because the Earth's atmosphere doesn't have a hard edge to it. It does extend higher up into these orbits, and even at the 550-kilometer altitude, satellites there will experience drag, such that if they didn't keep themselves at that altitude, then in the space of 5 years or so, they would re-enter by themselves. Just the accumulated drag effect on them would bring them spiraling down over a 5-year period. And that's one of the attractions of low Earth orbit, is that satellites, debris and so on in that orbit will gradually re-enter. If the satellite dies, for example, well, you just have to avoid the corpse of the satellite going around the Earth, but it will re-enter eventually. It's not true for OneWeb. The OneWeb satellites up at 1,200 kilometers are high enough up that the atmosphere there is significantly thinner, and therefore you're looking at a couple of centuries or so for re-entry, which is rather frowned on. So I don't know why OneWeb have gone for that high altitude approach. And there's another good reason I'll come to later on as to why it's much better if you keep the satellites down below 650 kilometers. So phase 2 has got to be half done by November 2024 and finished by November 2027. Now, at the rate that Elon Musk is getting these satellites up there, I don't think either of those deadlines are going to be a problem for him. What is slowing him down slightly is, first of all, he's facing some legal and environmental challenges. He's got some challenges at his Boca Chica launch site in Texas at the moment because of potential environmental threat to the wildlife park that he built his spaceport next to. And also there's a problem at the moment because, as I'm sure many of you are aware, there is a world shortage of silicon chips at the moment. It's not that there aren't any, but there aren't enough of them, and they're rather expensive, even to the extent that some car manufacturers have taken some of their electronic systems and converted them back into analog speedometers, for example. They could rather sell the car with an analog speedometer than a fancy digital display on the electronic dashboard in the car. So Elon Musk is actually being slowed down in his launches because of shortages of electronic components. Phase 3 here hasn't yet been approved by the FCC. Now, this is partly because of some of the legal challenges over phases 1 and 2. And the getting phase 3 approval is probably going to be done only once the legal challenges and issues have been sorted out with phases 1 and 2. Okay, so what sort of thing will we see? Well, this graph, it's a bit busy, I know, but what it shows is this is the number of satellites per 100 square degrees as seen looking up at the zenith. And along here, we've got at the bottom, we've got what's my cursor? We've got here the latitude, and it's the same north and south because the orbit's sort of symmetric above and below the equator. And so we've got phase 1 in blue, phase 2 in yellow, phase 3 in red. So what we can see here is that if you were to look up at the zenith at 52 degrees, let's say 54 degrees north here, you're going to have something like 0.15 of a satellite in 100 square degrees. It doesn't sound like very much to have a bit of a satellite in 100 square degrees, but you have to. This is based on just the Starlink satellites for one thing. So there are going to be the other satellite companies, but not only that, we've got the other issue is the illumination. You must take this into account, because if the satellite is illuminated by sunlight, you might see it. If the sun is depressed a long way down below the horizon, middle of the night in winter, for example, then the satellite may not be illuminated. So it may be there, but you can't see it. So this graph shows satellites that are there, not necessarily those that are visible. As you can see, if you're at about 52 degrees north, then once if he gets the approval for phase 3, you're talking about something like 1.6 satellites per 100 square degrees. Now, you might be thinking, well, what is 100 square degrees? Just to give you a feel for that, the square of Pegasus has got an area of 207.4 square degrees. So 1.6 satellites per 100 square degrees at the zenith means that if all of these phase 3 satellites are launched as well, means that any given instant you will have 3 satellites traversing the square of Pegasus at the zenith, if they're illuminated. The Orion, the 2 quadrilaterals that form Orion above and below the belt, they total 81.8 square degrees. So that gives you a feel. The bowl of the Big Dipper is 43.7 square degrees. Either way, you can see that just taking into account here these Starlink satellites, if they are all approved, you can see that's quite a lot of satellites crisscrossing the sky. So what do these satellites look like? This is the satellites here inside the fairing of the launcher. There are typically 60 of them, although sometimes there are fewer of them and the launch is shared with other satellites. But this is a full complement of Starlink satellites only. IKEA flat packed, mounted on rails, so that once the fairings come away in orbit, these satellites are just spring ejected off into space. They start out by unfolding the solar panel, which is about 3 meters long, I think, and starts out initially in a low Earth orbit, a lower Earth orbit than the mission orbit. They start out at 290 kilometers in this open book configuration here. And the reason for that is that, first of all, they use the lower orbit because at that level, if the satellite has launched and is dead, then the satellite will re-enter in a couple of 3 weeks or so because of an orbital drag. And the reason why it's in the open book configuration is that if the satellite, as SpaceX obviously hope will be the case most of the time, they orient the satellite so that the solar panel is parallel to the ground, so that you have minimum drag on the satellite. So it's a toss-up between the two. If the satellite is dead, you want more drag, but if as they're hoping most of them work, you want minimum drag. Then if the satellite's checked out and all the electronics works, everything's fine, they then have a thruster on board the satellite and they move it up to its operational orbit of 550 kilometers or something like that. And once they get there, or when they're on the way there, they raise into what they call the shark fin configuration like this, with the solar panel at right angle to the body of the satellite. Now, looking at the underside of the satellite over here where it says visors deployed, I'll come back to the visors a bit later on, but this is what they look like, and their intention is to cast a shadow on the underside of the satellite. These are the antennae underneath, and they're quite shiny, so they basically keep those in the dark. The idea being to try and reduce the reflections down to the ground. I'll come back to that. So at the moment, they've launched Starlink's version 0.9 and 1.0, and I think they've just started launching, I think it's 1.2 or 2.1, I can't remember. The initial ones they sent up have all now re-entered. They're up there as tests, and they've all come down again. they suggest that 95% of them were destroyed on re-entry. So there may be some bits of the early few satellites around. But all of the later ones were designed to be completely destroyed on re-entry, that they completely vaporized in the upper atmosphere. They tried covering one of the satellites' undersides in black, special matte black paint, so that they didn't reflect sunlight. It only dropped the brightness by about 0.9 of a magnitude, so 0.8 of a magnitude, which wasn't very successful at all. The other problem is that when you make the satellites black, they absorb any light that falls on them, and so the satellite gets warm, and it shortens their working life. And in fact, the problem was sufficiently great that only one satellite was ever tested this way. So what they then moved her to do was to trial VisarSat, and they were so convinced really with that VisarSat would work for them, casting a shadow on the underside, that they've more or less adopted this now, and just about everyone that's launched has visors on the edge of the satellite casting a shadow on the underside. But the satellites are still at about 6th magnitude, sometimes a little brighter, sometimes a little fainter. But that means that if you've got really good eyesight, dark skies area, you might just see some of these satellites. Of course, the thing is, on their way up from their initial insertion orbit up to their mission orbit, they will be brighter. And similarly, towards the end of their life, when they come down, they will be brighter. They have Hall effect thrusters using krypton gas for keeping themselves in position, and also at the end of their life, they use remaining gas to deorbit and come down faster. So at 550 kilometers, it would take 5 years. So they use a little bit of the gas. They reserve some of the gas to slow it down. And I'll come back to that later. But they also use it for maneuvering the satellite around others. They've got these really fancy antennae underneath that have steerable beams to be able to point to different places down on the Earth's surface. And they've got, sorry, I said 3 meter long, 9 meter long solar panel. They've got a star tracker system to make sure they can accurately point the satellite. And they're also uploaded with data from the US Department of Defense, so that the satellites allegedly can autonomously avoid a collision with other satellites. This remains to be seen, of course, especially if the satellite fails in some way. Now, you have to bear in mind that in the olden days, when you had the communication satellites up in geosynchronous orbit or geostationary orbit, at that distance of 35,000 or so kilometers, a satellite there could see roughly 40% of the Earth's surface. 40% of the Earth's surface means you didn't actually need many of them to be able to get total global coverage. With these satellites down at low levels, 550 kilometers, for example, they can only see about 4% of the Earth's surface, which means that you've got to have a network of them and lots of them to be able to get global coverage. So this is the reason why satellites in low Earth orbit have to have these mega constellations. What is being done now with the Starlinks, and this is the latest development, is they're adding laser communications, satellite to satellite to satellite, so that if you have an internet signal, you've made a request for a web page that's beamed up to a satellite passing over your head, and you want to get the web page from a server down in Sydney, then instead of it being beamed through optic fiber over the Earth's surface, it goes up to the satellite. It goes satellite to satellite using laser beams to sort of daisy chain your signal, your request from satellite to satellite. And then whichever satellite happens to be passing over Sydney then sends the signal down to Sydney, where your web page is selected and sent back on its return journey. Bear in mind that if you've got optic fiber made of glass, the speed of light in glass is about 2/3 that of the speed of light in a vacuum. So in principle, it means that you could actually make the communication faster with a much smaller latency than you would have using optic fiber on the ground. You still have to have, in both cases, you're going to have some electronics there to pick up, pass on, and repeat the signal and pass it on to the next satellite, or from one chunk of optic fiber to a next length of optic fiber. Either way, these are going to be electronic overheads, but either way, the fact that the speed the signal travels at 1.5 times faster in space means that you've got shorter latency. Some people have been reporting speeds of 400 megabits a second communicating with the Starlink satellites. So what do these satellite dishes look like? Now, this is an old picture. They have in fact started now to produce a square and slightly smaller version of this dish. SpaceX have applied for a license for up to 1 million ground stations, 1 million of these dishes in the United States. And the dishes were given the numerous nickname in true Elon Musk fashion, Dishy McFlatface, and it's 19 inches across. It's about the size of an American-sized pizza, a small American-sized pizza at that. Now, it's expensive. You have to buy in by buying the kit first of all at $499, and then it's $99 a month for the broadband. If you live in a log cabin out in the wilds, where there is no chance that you're going to get an optic fiber delivered to your door anytime soon, then this is perhaps a good solution, especially if you've got the log cabin as your weekend getaway, and you've got all these bored kids bouncing off the walls, wondering what to do. You've got a way at least of keeping entertained and streaming TV and things like that. The dish is actually steerable. It does steer slightly, but also not only that, but the dish is also a phased array antenna similar to the one that's on the underside of the satellites, so that even if the dish were to stay in the same place, it can effectively use phasing of the radio signals to produce a reception beam in a particular direction. They're fairly sophisticated pieces of kit. The economics is questionable because when they first came out, they cost about $1,500 to make. And the other problem is that customers in hot temperatures down in Arizona, living somewhere in the desert outside Phoenix or something like that, they found that these satellite dishes shut down, the electronics shut down at a certain temperature. So that's part of the reason why they produced the smaller version, the newer version, because they have redesigned them basically to not be temperature sensitive. The other problem you have is that at the frequency they work at, rain, snow, pigeon droppings, trees, all of these things can quite easily obscure the signal. So they say that the dishes have to be mounted high, roof of your house, or if you've got flat ground with no trees around, that would do. But people have been reporting problems with pigeons settling on them because they're warm, of course, because the electronics inside, and that really messes things up. This is the router, this odd-shaped thing down here. I haven't quite figured out how it stands up. I suspect it must be triangular on the base or something, but it's basically provided again as part of the kit from SpaceX. And yes, these speeds I quote here have now been exceeded. As more and more satellites are launched, the network becomes more complete, better coverage, so people will have a better service later on. And the initial name given it was the better than nothing beta. So that's the satellites. Now, one of the issues is collision avoidance. That they mustn't collide with each other. I'm sure you're aware that if something's traveling at typically 7 to 15 kilometers a second in orbit, that's a lot of energy. A 1 kilogram CubeSat has energy of about 6 kilograms of TNT at 7 kilometers per second. So you can imagine if a 1 kilometer CubeSat collides with another satellite at that sort of speed, there's not a lot left of either of them. That causes a lot of debris. And there are already estimates of the huge amounts of debris there are up there. something that's bigger than about 4 inches, 34,000 pieces of debris bigger than about 4 inches, 1 centimeter to 10 centimeters. So this is marble size up to 4 inches, 900,000 pieces. And then there's the stuff of a millimeter or up to a centimeter, 128,000. The Americans are more laid back in the descriptions, bigger than a softball, bigger than a marble, too small to track. Either way, the numbers are huge, whichever way you look at it. It's important, therefore, given the amount of debris that's up there already, that whatever you do, you need to make sure that you don't add to that debris. Hence the moves to try and have these satellites maneuver to avoid each other. SpaceX have claimed that the satellites will be able to autonomously avoid each other, but there was an incident in September 2019 where a Starlink satellite nearly collided with an ESA weather satellite. Luckily, that was resolved by ESA moving their satellite rather than the Starlink satellite moving. But in addition to making sure your satellites don't collide with each other, which is pretty much down to space traffic management, you need to make sure the satellites aren't going to explode. Batteries, notorious, carry a high amount of energy inside the batteries. They're obviously being charged and discharged, as the satellite goes into the dark and so on. It's draining the battery, and back in the sunlight, it's being charged up again. So it's quite a work cycle on the batteries. They can explode, so you have to design them so that there's very little risk that they'll do that. The electronic components themselves maybe can explode. I'm sure those of you who are into electronics will know that capacitors, some capacitors are prone to going that way. And of course, if you're carrying gas fuel to be able to maneuver your satellites, then there's a chance that you've got a compressed gas component on board that could explode if it was struck by a micrometeorite or something like that, or another piece of debris. So that's an issue that you have to be careful about. Then you come to the issue of deorbiting. One of the other things, quite apart from saying how many satellites they want to put up and what orbits they're going to be in and what frequency bands they want to use, they also have to say how they're going to bring the satellite down at the end. So in a 550-kilometer orbit, they've said drag forces will bring it down within 5 years if the satellite just dies in orbit. If it doesn't, they will use remaining fuel to lower perigee. So they burn the fuel at the apogee point to slow it down, which reduces the perigee height. Eventually, the perigee height will cause enough drag on the satellite to cause it to re-enter. They expect it to take a few weeks to do that, perhaps 4 or 5 weeks, something like that. They also reorient the satellite so that whereas on the way up they want to minimize the amount of drag on the satellite, they now want to maximize the amount of drag on the satellite. So they turn it flat on to the direction of travel. They spin down reaction wheels, drain batteries, and so on and so on. And in a matter of a fairly short space of time, a couple of months at most, the satellite will re-enter and be destroyed, which doesn't address completely what happens if the satellite becomes unresponsive, because if the satellite dies, it'll take 5 years to come down. But now what you've got is a fairly big cannonball spiraling slowly down through the altitude over a 5-year period. And given that you're talking about one orbit every 90 minutes, that's a lot of orbits before the thing finally gets dragged enough to be forced to re-enter. So you've got to think here that since the typical life of these satellites is 5 to 7 years, if Musk does get his request to put 42,000 in orbit, for 5 to 7 years, that will mean that there will be between 500 and 700 a month coming down, and 500 to 700 per month going up to replace them. You've got the pollution from the launch vehicles, and you've got the re-entry, and already there are papers being published showing that the aluminium powder being scattered into the Earth's upper atmosphere will have an effect on, first of all, sky brightness at night. There are already papers being published to show that the sky is already noticeably brighter than, for example, when they moved the telescopes from London down to Herstmonceux, the criteria for sky darkness is already broken by how bright the sky is now. So this is literally just caused by the amount of debris there is out there in space, and possibly also to be made worse by all of the fine particulate matter that will be scattered into the upper atmosphere by re-entry. Think about all those rare earth metals, the ones, the lanthanum and cobalt and all of these that are commonly used in electronics, and these are all being squandered. They're all being, again, vaporized into the upper atmosphere. At any one time, even if you only count half of those satellites as being brightish on the way up or down, you're going to have something like 600 fairly bright satellites in the sky. So they have said that they will try to orient the solar panels for minimum interference with observations from the ground, but during deorbit phase or even raising to orbit phase, the solar panels are going to be aligned to minimize or maximize drag, which isn't necessarily going to be good for reducing reflections. And again, working the numbers, if there are something like 600 satellites re-entering the Earth's atmosphere each month, that's 20 a day somewhere around the world. This is just for Starlink satellites. One company's ambitions for 42,000 in orbit. If other companies get to put theirs up and there are 100,000 satellites in orbit in a decade to 15 years' time, then that's a lot of satellites going up, coming down, and streaking across the sky as they re-enter. You've got the Kessler syndrome. You've got the Kessler syndrome, which is, if you may remember, there was the film Gravity with George Clooney and Sandra Bullock. And this had the potential for a chain reaction of space debris collisions. Now, I've been talking to Hugh Lewis at the University of Southampton. He's a significant expert in space debris. He seems to feel that from his modeling that even if these satellites did collide with each other, then you would have, because they're in low Earth orbit where there's atmospheric drag, that you wouldn't have a persistent problem. Well, persistent problem, okay, but I think that if you were to have collisions and causing a spike in debris, either because of collisions or because the Russians are blowing more satellites up, then you've got a spike in debris that could cause problems for a few years. And you may not get to the point where there's enough of a problem to cause a chain reaction, but you could have enough of a problem that it makes space an unsafe place to be. So moving over to the radio astronomy side of it, this represents different frequencies here across the top. The frequency, and this shows it's just part of it, the allocation of different bands of this to astronomy, to emergency services, to here the time signal and various other things like that. Parts of this are reserved for radio astronomy. And here we've got Starlink's blue communications. This is the signal coming from the satellite down to the Earth, and the green one here is where they send command signals up to the satellite, allocated by the FCC on behalf of ITU. Now, radio astronomy is a real problem because I talked earlier on about the satellites may be there but not visible because they're not illuminated by sunlight, and I'll come on to that a bit later. But of course, with radio astronomy, it doesn't matter about the illumination of the satellite. These things are broadcasting radio signals down. It's like having orbiting searchlights, if you like. The other thing is that you've got reserved parts of the frequency spectrum here. These are the areas that are of particular interest. Certain molecules are of particular interest, water and hydroxyl and cyanide and things like that. But of course, the other problem is that if you're observing a distant galaxy, for example, it could be redshifted, which means that the signal that you're receiving isn't in this band anyway. It's shifted somewhere else. So that's another problem. Now, on the ground, the big radio observatories often have radio quiet zones around them, where you're not allowed to bring an active mobile phone on site, for example. They have detectors by the side of the road so that they can track an approaching vehicle, and they put warnings up saying, turn off your mobile phone because you'll drown out the equipment. The other problem you've got here is the satellites themselves, even if they were not to be actively broadcasting, there's electronics inside, and electronics produces an electronic noise, if you like, as a byproduct of the fact that their electrons are moving through wires. So the radio signals are, even though they're very small, are still enough to be detected by some of the larger arrays. The square kilometer array, for example, is capable of passively detecting satellites that aren't broadcasting. So you've got to take that into account as well. So what SpaceX have said they will do is that when they're passing over the large radio observatories, they will effectively steer the beams away from the site. Or, in an extreme case, they will stop transmitting altogether. So effectively, there's a dead spot over the Earth where if you want a Starlink satellite dish, you're out of luck because it's going to be turned off going over you. So a little bit here about the geometry of the visibility. So we've got, this thing is entirely to scale. This is the Earth's curvature. This is a 1,000 kilometer altitude orbit. The only thing that's not to scale clearly is this observatory, which would be a few dozen kilometers high if this were the case. Most professional astronomers don't look down much below 30 degrees above the horizon. So what's being looked at here is the cone, the observing cone that's within 60 degrees of the zenith above the observatory. Now we've got the sun here, 15 degrees below the horizon. So clearly any satellites that are above this purple line are illuminated. Any that are below the purple line are in shadow. So you've got here, all of those here above the observatory are visible. In particular, you have a problem with the ones over here because here the sun is making a glancing reflection off the underside of the satellites, and therefore below 30 degrees above the horizon, you've got a lot of satellites that may be specularly reflecting that light and being bright. When the satellite gets further down, so here I've got it 30 degrees below the horizon, you can see that part of this cone is now no longer illuminated. So satellites that are in this part here are no longer visible because they're now in the Earth's shadow, whereas these here are still illuminated, as are the ones here below the 30 degrees in the sunward direction. So this applies clearly after sunset and before dawn, before sunrise. So just very sure I'm teaching Granny to suck eggs here, but this is just if the green plane here is you as the observer, and this is your horizon around here. This is pointing up here towards the pole star. This is set up for Birmingham at 52.5 degrees north. You've got the tropics, 23.4 degrees either side of the celestial equator, and all this is designed to show is that in midsummer, the sun only gets to be in Birmingham only gets to be 14.1 degrees below the northern horizon. Whereas in midwinter, it gets to be down here at 60.9 degrees below the northern horizon. So you can see that you have much more of a problem, comparing this with my previous pair of diagrams, you have much more of a problem in the summer than you do in the winter, because the sun spends almost none of its time below 50, well in this case, none of its time below 15 degrees in the middle of summer. In the middle of winter, it gets down below 15 degrees fairly quickly. So this leads you to be able to produce a graph like this, which shows you, and down here we've got negative degrees, 12 degrees below the horizon, going down to 48 degrees below the horizon, different colors for different orbital altitudes. And this is the percentage of satellites in the sky that would be visible versus the elevation of the sun. So what you can see is that if you have satellites down at, say, 550 kilometers, then only half of them are visible by the time you get down to about 23 degrees below the horizon. Whereas if you've got satellites here up at 1,110 kilometers, and I can't think why I chose that number, but it's very close to the OneWeb altitude, here you've got more like 90% of the OneWeb satellites would still be visible at 23 degrees below the horizon. So this is part of the aim why it's been recommended that satellite operators who want to launch mega constellations put them into orbits that are low Earth orbits, much lower down than 650 kilometers if you can, because these satellites here fall into the Earth's shadow much more quickly than the ones at the higher altitude. It's difficult to model the brightness. There has been, I'll skip over these fairly quickly. It's difficult to model the brightness because they're multifaceted and so on. And there have been estimates of brightness at 4.2 to 5.9 magnitude, but the visor is making them a little bit fainter than that, but not a lot. During orbit raising, some have been seen at between first and third magnitude, so they can be quite bright during orbit raising and presumably also end of life and they're coming back down again. The satellites are being continuously realigned using a magnetotorquer, which is basically using coils on the satellite, 3 coils, XYZ coils, with current passing through them, to react against the Earth's magnetic field to provide a turning force on the satellite. So that way they can turn the satellite without using fuel up. So this comes to sort of the end of the first part of the talk, really, where this is a cut down version of the table I put in my FAS newsletter article. If you've got a satellite, let's just take an example, a satellite, and you can see a satellite that's 50 degrees above the horizon, and it's at an altitude of 550 kilometers, then its distance will be nearly 700 kilometers away. And obviously, the further down towards the horizon you look, the further the satellite will be away from you. So take 50 degrees, about 700 kilometers away. Its angular size will be about 2.7 arc seconds in diameter, and its velocity across the sky, its angular velocity in arc minutes per second, is between about 31 and 37 arc minutes per second. So if you know that, these speeds across the sky, and you know roughly how many satellites you're expecting in the sky, and you can use my spiky graph from several slides earlier to give you an estimate of the number of satellites per 100 square degrees. That one, you can get a feel of the satellite density. You can plug the numbers into this equation here, assuming that all of the satellites are illuminated, so you're not looking into the shadowed part of the cone away from sunset or away from sunrise. And so here you've got some typical sizes here. If you've got a pair of 10 by 50 binoculars on a mount pointed in one particular direction and you looked for 10 minutes, you would probably see half a dozen satellites pass through your field of view. So the big problem is with the professional telescopes, things like the LSST at the Vera Rubin Observatory. It's a wide field camera telescope, and typically this will capture about 7 satellites if it were to expose for 10 minutes. Typically its exposures are shorter than that, however. But that's still not good because it has a very, very sensitive camera, can see down to, I think, 23rd magnitude with one of its exposures. So you can well imagine that one of these satellites passes overhead at 7th magnitude. It's very, very bright compared to what these sensors are capable of picking up. If you're an amateur observer, you might have a 1 degree field of view, and so there's a chance that in a 40-minute period you will see 3 satellites. So less of a problem for amateurs who are just observing, because first of all, your eye can work out what the satellite is and you can ignore it. It's more of a problem if you're imaging, but even so, the smaller field of view means that you usually can do something about it. And of course, as an amateur, your time is your own, and I know it's inconvenient, but in principle, you can shift your observation to suit yourself, whereas professionals booking time on professional telescopes, they have a slot to get their observations done in, and it's not always easy to work around. So this is a simulator that I produced some time ago, and what I'll do is I'll show you the simulator, and then we'll take a couple of minutes break, and then I'll come back and go on for another 20 minutes. I think, would that be all right? and I'll try and get through the rest of the talk in that. So I'll just show you this very quickly, and let's get it going first. I'll do this behind the scenes so it looks smooth. Hopefully you can all see that. Can somebody nod if you can see that, the Earth?
Yep,
yep,
I can
good.
see it.
Okay, thanks. So here we've got the Earth, and it's relatively crude as a demonstration, but I can zoom in here with the Earth and get closer, and I can move up and down, so on. I can also alter the solar angle, so you can simulate what time of year it is, and you can turn the Earth on and off, and turn animation off, and so on. If I turn on the phase 1 and 2 satellites, so this is the initial 12,000, this is what's going to be there. They're moving a little faster than they should do, so let me just slow that down. So this is typically the speed of the satellites as they move over the Earth. It's obviously, on this scale, it's very slow, but if I move up, I didn't have time to implement a fancy view. I also haven't worked out yet how to scale the satellite sizes. Let's turn them down a bit. So you can see this is typical of the speed that you will see of the satellites going over. Now you might wonder why it is that there is this this band here. This is because a lot of the orbits have a 53-degree inclination. So this is where they're passing up at the uppermost part of their orbit over the 53-degree latitude before they head south again. And because there are so many of them, it looks almost like there's a barrier or a wall there that they don't go above. These up here are the polar ones, and the 70-degree inclination ones I talked about earlier. But you can see that at any instant, passing over the UK, there are going to be quite a lot of satellites. This is just the 12,000. If I also turn on the other 30,000, then you have, this is the ones in yellow. You can see also, looking at the side here, you can see a lot of these are at a lower altitude than the 550 kilometers. These are the 300 kilometer altitude satellites. So you can see here that you've got a lot of satellites passing over the Earth, over the UK. If you lived somewhere like Manchester or Stoke-on-Trent, I think it's 53 degrees north, that means that these are going to be directly overhead at the zenith. Further north, my geography is not great, but you're up about here somewhere, I think. Looking south, you'll see the concentration of satellites slightly further south than the zenith from where you are. Okay, that link, I'll stop sharing this and I'll go back to my slide. This link here is available for anybody to use. You have to make sure you get the case sensitivity right. I've also got here for fun. I was asked a question about the moon. Somebody said to me, at what point do you first notice that the moon is no longer a full moon? How long does it take after a full moon? How many hours before you can see it darker on one side? So I did a simulator of moon phases, which again, you can go and play with as well. Okay, I suggest if anybody wants a quick break, and then we can come back and I'll carry on with the talk. I've got about another 10 slides, but I will go through them very quickly. Is that okay, Neil?
Yeah, that's fine, Paul. Just to mention, I saw about a month ago on the BBC site that China had announced in the next few years they're going to launch 13,000 constellations to provide high-speed internet across the whole of China. That's
right, yes. They were the ones in my table earlier on, GW, Guang or something. I forget the name now. Yeah, they are. There's also the Russians are planning their sphere constellation, Megaconstellation as well. And Of course, there are going to be constellations you may not know about because they could be military. So that's always a possibility that you will never find out about them, other than the fact that they will obviously be detected by being tracked post-launch.
Yeah.
I'm happy to answer questions for the next few minutes if anybody wants to answer questions while people go for a comfort break or whatever the phrase is. I got into this, I suppose, first came to my attention January last year, and it struck me as horrendous what was going to happen. And the first meeting of the Royal Astronomical Society about it, and this is like a committee meeting, was held on the 31st of January last year, and in Burlington House, and we had people from ESO, people from all over the UK. We also had some representatives from OneWeb and from SpaceX. Patricia Cooper was there. She's there, sort of, I think, international liaison. And it was a very good discussion, but the more I heard, the more horrified I became. My initial reaction was, how dare this one man, one billionaire, decide to put up all these satellites? It's going to ruin the careers and the vocations of so many thousands of astronomers. Plus the danger to space, the risk of space debris, because I know that they say that they're going to make these satellites avoid each other, but that's all very well and good until they don't. And you could end up with these satellites being ground down over a period of a few years into orbital dust and debris around the Earth. You could end up with low Earth orbit that's unusable because of the debris there, because you've effectively got these really high velocity pellets of debris flying around the Earth. And not only then does it become dangerous for launching other satellites, even if you want them to be in a higher orbit above this shroud of dust. But of course, you can't put manned space stations into orbit safely. And even something like the James Webb Space Telescope that's being launched, good luck getting insurance on that if you've got to launch it up through a hailstorm to get it out beyond out to the Lagrangian point. And then, of course, what about all the things like the Cassini type probes and the probes that are going off to look at other planets? They've got to run the gauntlet of all this debris. It could have a serious problem on our access to space and sustainable use of space. And there have been quite a lot of conferences going on to discuss ways to make space sustainable. And that's why there's also been a lot of focus on companies that are launching satellites whose job is to bring the big bits down, on the basis that if you bring the big bits down, you end up with less chance of that big lump being broken down into lots and lots and lots of small bits. I've been asked a question here by Alexander Brown. What's the dimensions of a Starlink satellite? I have to say I don't know exactly, but from the picture I showed earlier on with the solar panel, about 9 meters long, I would guess that the satellite is about 1 meter by about ½ meter, something like that. That's the body of the satellite. But the solar panel sticks about 9 meters up above that when it's in the shark fin configuration.
I mean, just to add, from my own thing, I think, however bad Starlink might be, that the big worry is that's the door, and once it's opened, as in China, they're not asking NASA or anybody how they configure them or what have you. They're just gone ahead and done them. And for the prices you were mentioning, you've got small countries, you know, Bulgaria will say, oh yeah, we'll put up, you know, 5,000 of them. And once the door's opened, you're not stopping it. And assuming somebody can launch them, and you bet your life, you know, there will be people in the world who are prepared to launch these things. Nobody can stop them.
Exactly, because this is all down to people really pursuing this for commercial purposes. At the end of the day, Elon Musk is going to make a ton of money out of this. I mean, I don't know whether you're aware, Elon Musk. I mean, he started out first, made his money setting up a small company for doing online payment called X, and X eventually took over or became part of, I'm not quite sure which, PayPal. And so Elon Musk's initial bunch of money came when X was sold to PayPal. So he used that money to set up the Tesla battery manufacturing company and car manufacturing company. So Elon Musk is Tesla, and he made so much money from both PayPal and from Tesla that he started up SpaceX. And obviously he's gone from strength to strength with that. His intention apparently is an altruistic one. He wants human beings to be on Mars. It's one of his dreams. And so he's basically using Starlink to fund his aspirations of having humanity on Mars. I have seen some reports in the press that he's said that if he gets humans to Mars, they won't follow any Earth laws, which is interesting because that would be in direct contravention of the United Nations international treaties that say that nobody, no nation, no individual can own any celestial body or part of it. And he would then be required to follow at least some international laws. But he said, "Oh no, we'll do it my way." He's a maverick in both the good and bad sense of the word. He's certainly a genius. He's certainly got some grand visions, and he's prepared to put his money where his mouth is. But at the same time, we're living in a time when technology is moving faster than laws and treaties can keep up with it. So you actually have a situation now where he's going to have a very large boot in the door by the time the treaties catch up with it. And so how do you then tell a man who's launched, say, 10,000 satellites, I'm sorry, but you've got to take them down again? It's very difficult to do, not without lots of lawsuits and all those sorts of things flying backwards and forwards. There are challenges. There are challenges on environmental grounds. Things like, for example, when they re-enter and they scatter material into the upper atmosphere, how does that affect the Earth? How does it affect the night sky? How do all these satellites up there affect birds navigating and things like that? So there are all these sorts of questions. And the part of the reason why the FCC was able to get it on, I won't presuppose the last part of my talk. Shall I carry on?
Yep, let's launch off.
Okay. So let's talk about who's affected. So first of all, there's the professional astronomers. In particular, people like the Large Space Telescope, the Vera Rubin Telescope, looking out for things like near-Earth asteroids and comets. You won't see them so easily if you've got all these satellites in regions down closer to the sun in the sky. So if there's an asteroid coming at you from behind the sun or a comet coming at you from behind the sun, you're much less likely to see it. The large surveys generally tend to be with the wide field cameras, the camera telescopes. They're going to be affected because it's going to be much harder to avoid having these satellites passing through the image. If you've got an image, at least you can see where the satellite is. You may be able to do something to remove the satellite from the image. If you're taking a spectrum of some object and the satellite passes through the field of view, the spectrum of the satellite, or I should say more likely the spectrum of the sun reflected off the satellite, is going to be intermingled with the spectrum of your object, and therefore that's going to cause pollution of the spectrum, and you may not even know that your spectrum has been polluted, and there's no way to remove it. You just have to chuck your spectrum away. So this was a simulation of what a streak across one of the Vera Rubin telescope's sensors will look like. You've got a problem here because you've got, let's get back to my notes. You've got a problem here because they use CCD sensors. Now, CCD sensors are very sensitive, but the structure of the electronics that makes up the sensor means that if you get a very, very bright streak across there, you will max out the sensitivity of the pixels in that streak. You run the risk that not only can you not recover what was under the streak, but you also can produce electronic artifacts such as these stripes the other side, caused by signals in the sensor getting to parts of the sensor they shouldn't be able to because it's so strong. It's like an overflow process, if you like. So the CCDs are very good because they're very sensitive, but they do have this problem. Not only that, but with the LSST, you take a picture of part of the sky, then you have a gap of a few seconds, and then you take another picture of the same part of the sky, gap of a few seconds, and you move on to an adjacent part of the sky, and you take two pictures there as well. So every piece of the sky is photographed twice. Now, one of the problems with saturating the detector is that sometimes the sensor doesn't clear back to black completely between one picture and another if there was a bright streak across it. So you may see a ghost of the streak in the subsequent image. So that's the problem. Now, if they said with the Vera Rubin telescope, if you can get the satellites down below about 9th magnitude, you may be able to get this streak to be faint enough that you don't max out the sensitivity of the pixels, and therefore you may be able to subtract the streak away and recover what's underneath. It won't be perfect. You're still going to have some anomalies in the background noise and things like that, but you may be able to get rid of part of it, and that's part of some of the work that's being done. I'll come on to that. So this is also satellites in orbit. It's not just a problem for ground-based astronomy, although it's going to be a big problem for ground-based astronomy. You've got here, this is again to scale. This is the curvature of the Earth. These are satellites here up at the 5, 40, 50, 60, 70 kilometer altitude. And this green box shows that in expanded view with the dotted lines showing the range of altitudes for the Hubble Space Telescope. So you've got some potential for collision or debris. Already, they're seeing some of the HST images being spoiled. If you can imagine being the Hubble Space Telescope just here, for example, looking at an angle. I was about to put my hand on my screen and show you. Of course, you can't see that. if you've got the Hubble Space Telescope looking in this direction, then you're looking through these layers of satellite orbits here. So if you're looking at an angle that's almost parallel to the Earth's surface, parallel to the orbit, then you've got potential for the HST to have a lot of satellites in its field of view. Many of them will be out of focus, so it's not like there are points of light that can be removed. Already, they are seeing 2.5% of the images being spoiled, with the potential for 20% of them being spoiled with 60,000 satellites in orbit. The Vera Rubin telescope, by the way, they haven't seen first light on that telescope yet. It's still in the construction, and they're already predicting that when first light comes, something like 40% of all of its images will be damaged by satellite trails across it. You've got a couple of others, the Cheops satellite, Sun Synchronous Orbit, looking quite a long way away from the Sun, and therefore it's also got the potential to have satellites crossing through its field of view. And the WISE satellite here at 525 kilometers, so that's only a little lower than this. It's going to potentially have satellites in its field of view as well. So some space-based astronomy will be affected as well. Clearly not the James Webb Space Telescope, because that's going to be out at the Lagrange point, well out the way. So you've got a radio and infrared. Satellites don't have to be illuminated. They are emitting radio waves, and that's what you're picking up. So as I say, the analogy is orbiting searchlights, plus their own electronic noise. you've got the shifting of emission lines from a redshifted galaxy into parts of the band that aren't protected, and so you may have a problem there. You've got also thermal lag. For infrared astronomy, you may have a satellite that is not in the illuminated part of the sky, but it could be partly in the dark part of the sky. But if the satellite has been in sunlight, it may still be cooling down, and therefore maybe an infrared source, even if it's not an optical source. The other problem you've got with radio astronomy is that your antennae are never perfect. They produce hopefully a pencil thin beam pointing in the direction you want, but there are often side lobes to the beam, side lobes to the beam that means that you could have something off to one side that is visible to your radio receiver. And similarly for the transmitter, they may be transmitting in one direction, but you can have a transmission side lobe, which means that, if you like, part of the signal leaks out sideways away from the main beam. This has always been a problem and is always going to be a problem. It's inherent in the design of antennae. Not only do that, but you may be attempting to broadcast in a very narrow frequency band, but you do also get side bands. Again, it's not possible to force all of the energy into one specific frequency. You do get some side bands, and so you may be broadcasting in one particular frequency. Maybe the side band is interfering with a radio observatory. So these are going to be a problem, I think, potentially more of a problem to the radio astronomers than to the optical astronomers. Amateur astronomy is going to be affected, but I think to a lesser extent. The instruments are generally smaller field of view, and also amateurs tend to use a lot of off-the-shelf cameras, DSLRs, with CMOS sensors in them. CMOS sensors are much less likely to be affected. They don't have the same problems that CCD sensors have. So there's much more potential to remove the trails or mask the trails out in the images that you take. Some amateurs do use CCD sensors. You can get some relatively expensive ones, but by relatively inexpensive, we're talking about a couple of £3,000 or so. Perhaps, maybe I'm out of touch there, but somebody who's really keen may buy one, and they potentially will have problems with their observations. There are some software applications that are going to be made available, and I'll come on to those in a minute, that are going to be able to perhaps help with the problem. Here also I refer to, if you know when the satellite's going to cross your field of view, then maybe it's possible to have a shutter that will automatically close and block off the sky for the couple of seconds it might take for the satellite to pass through your field of view. So you've lost a couple of seconds exposure, but on the other hand, you haven't got a streak through it. Clearly, you need to know exactly when the satellites are going to pass through your field of view. And also for amateur radio observatories, even if SpaceX do decide to steer beams away from the large square kilometer array and Jodrell Bank type observatories, they're not going to do it for Joe Bloggs with his radio telescope in his back garden, his radio antenna in his back garden. It's just not going to happen. And I know these satellites are powerful enough that that almost certainly they're going to affect amateur radio astronomy. From the public point of view, it's still something of a curiosity. I'm noticing actually that there's a lot less in the newspapers. The novelty has worn off slightly. When first of all Starlinks were being launched, and there was this chain of dots across the sky as they were being launched, people phoning in reports of UFOs and things like that. There was a lot of media interest, but I think it's beginning to dawn on the newspapers, in particular the ones that aren't the red tops, that this is going to be a serious problem. Mostly, however, they're not so much interested in the problems to astronomy. Mostly, they're interested in the problems for space debris. So you'll see much more about that. And to some extent, I think that much as I love astronomy and I love the whole philosophy and the science and all of the beauty of astronomy, I think in some ways the best lever that we can use to get some control over these is with the space debris aspect and not the astronomy aspect. These satellites are still going to be visible on the way up and on the way down. So even if they're below naked eye brightness, mostly when they're on orbit and mission, then you're still going to see them on the way up and on the way down. So you could be talking about, if you take all of them, not just Starlink, you could be talking about 1,000 or more satellites that are going to be visible coming up or down from their orbit. And it's a shame, because you remember the first time you looked through a telescope and you had this wow factor of seeing Saturn's rings or the Orion Nebula or something like that. And there's a risk that if you've got this pollution of the night sky by all these satellites, that you could lose young scientists, young astronomers of the future. So this is a little bit of a reference to an article I put in a more recent FAS newsletter. I attended the SATCON 2 conference, which was in July this year. I also then followed that with the Gnosis, which is a conference which is on the safe and the sustainable use of space, more satellite operator, space industry oriented than astronomy. And then I went to the, on all of these online, I attended the UN USA's Dark and Quiet Skies conference, which is the United Nations Office for Outer Space Affairs, UN USA. Dark and Quiet Skies. The first couple of days were about terrestrial light pollution. I didn't attend that because the whole thing was 5 days long and I couldn't give up all of 5 days. But the remaining couple of 3 days were about both satellites in space and also radio. One of the things that came out of SATCON 2 is that they're going to set up something called SatHub. At the moment, it's a working title, SatHub. They've already got something called Trailblazer in place. This is somewhere you can submit your damaged images, because they need images to train the software on, software that will detect the streaks and try to remove them, software that will try and model the way that satellites maybe tumble and the variations in the streak. Because a streak isn't necessarily going to be a straight line, maybe a slight arc. If the satellite is tumbling, then of course it's going to be a pulsating width and so on. So it's going to require lots of example images. There is a group set up jointly with the FAS, the BA, and the SPA, which was prompted by the Royal Astronomical Society, but this is an all-amateur group. And we've just started to do some work with Meredith Rawls of Washington University in the States, because she set up the Trailblazer project to try and organize UK amateurs to observe the satellites, to observe them so that we can model the brightness of satellites in different parts of their orbit, and also to try to get accurate position measurements so that if you know where the satellites are accurately, then you can start to avoid your observations clashing with when a satellite's going to pass through your field of view. So it will feed into software called Pass Predict down here that will help you to work out whether or not your observation is going to be affected, or maybe you'd be better off waiting 10 minutes and taking your image because then you won't have any satellites going through it. So Trail Mask is the one to try and remove the streaks, and Pass Predict is the one for trying to predict when satellites will be passing through your field of view. SatHub is going to be an open shop. Anyone who's got software expertise will be able to submit ideas, will be able to join into the software development. The software will be free to use for both professionals and amateurs. And it will be fed and kept up to date by all the observations that people make. There's always two sides to the story. because clearly a lot of people around the world would like to have good internet access, and so it's feeding into that really. So you've got to remember that much as there are people who don't want astronomy to be damaged and don't want the risk of space debris, there are a lot of people who want to be able to have international internet. The military in particular are very interested by it because for them it offers a communication route that is less likely to be interfered with. The Outer Space Treaty 1967 is the main one here, which basically says that nobody can own space or any celestial body. And really this treaty was put in place a long time ago, before the space race really started to get going. You have to remember this is only 10 years after Sputnik, and so the negotiations for this would have started only 7 or 8 years after Sputnik. And the big worry was that people were going to use space for putting up weapons of mass destruction into orbit. And so at the press of a button, not only did you have to worry about the ICBMs coming over the horizon, but you had to worry about perhaps nuclear bombs being dropped from orbit or something like that. This was a big worry back in those days. Space is still being used for military purposes. Obviously, reconnaissance satellites, surveillance satellites are military purposes. And you're now seeing, as in the issue with Russia recently, the testing of anti-satellite satellites. So satellites that carry harpoons or satellites that carry missiles. So this is not ruling out the prospect or the possibility of war in space, just weapons of mass destruction being carried in space. But basically, the Outer Space Treaty says everybody has to play nice. If someone's in trouble, you go and give them a hand. You need to have your systems open to inspection. Generally, people tend not to. You're responsible for your own activities in space. But there's no claim for sovereignty over space. Just when the Americans planted the flag on the moon, they could not claim that the moon is now American. There have been other treaties. The Bogota Declaration tried to claim slots in geosynchronous orbit. That didn't work. The Moon Treaty, 1979, they tried to bring celestial bodies and so on more under jurisdiction of the United Nations. But by 1979, this is here another 12 years after the Outer Space Treaty, by then countries are getting wise to the fact there's this space Klondike out there. There's all sorts of potential uses for space. They could see the potential for commercial, for scientific, for military use. And so nobody really, none of the big nations wanted to sign up to it. They felt it would be a bit like shooting themselves in the foot to deny yourself the use of parts of the moon, for example. Then Obama signed a treaty saying that US companies could own and sell resources extracted from the moon. So if you bring a bit of moon rock back, then that's fine. You can sell it and use it, but you don't own the bit of moon you got it from. Trump then, April last year, signed an executive order recognizing that private companies could claim and recover resources in space. But the worrying phrase he used here is, outer space is a legally and physically unique domain of human activity, and the United States does not view it as a global commons. In other words, if we get there first, we're going to claim it as ours. This is the sort of the land rush, the Oklahoma land rush days, where you rushed to grab a plot of land, and once you got there, it was yours. First come, first served approach. Well, this is where Trump is effectively saying, if we go up and we dominate certain orbits in space, well, we're not going to move over to let you put your satellites there. You've got to work around us. Or if we get to the moon, then we're going to claim it as ours or use it as ours, even though it doesn't legally belong to us. So this was really Trump staking a claim, if you like, and threatening to override part of the Outer Space Treaty. So how do we get here? The thing here is, this is the National Environmental Protection Act. Most US agencies, government agencies, are bound by the National Environmental Protection Act. If they are going to grant someone a license to build a pipeline or build a road or a tall building or something like that, then they have to go through an environmental risk assessment according to NEPA. Some agencies are exempt from that, and unfortunately the FCC is one of them, because FCC early on said, look, we allocate the frequencies, we regard things that happen to the orbits and when they're going to bring the satellites down again. We don't affect the terrestrial environment, and therefore we should be exempt. And so they were granted exemption from having to abide by NEPA. That clearly doesn't really wash anymore when you look at the pollution from the launches, when you look at the pollution in the upper atmosphere and the pollution of the night sky. The night sky doesn't currently count as part of the terrestrial environment. And yet when you've got astronauts in orbit around the Earth, clearly space is part of the human habitat now. There is perhaps a counter to the FCC here, which is that the Council on Environmental Quality have a regulation that says that every government agency must have its rules and regulations under continuous review. And there is an argument that since the FCC hasn't updated their rules and regulations for about 30 years, they should have updated their claim of exemption from NEPA long ago, because clearly megaconstellations changed the game somewhat. We've got SpaceX already getting military contracts on the use of Starlink. There's been talk about perhaps using Starlinks to provide links to control cruise missiles. They've already had experiments where they've refueled aircraft guided by signals from Starlink satellite. And of course, Donald Trump created the US Space Force to protect American and Allied forces' interests in space. So you've now got not only the political side of it, trying to claim parts of space, but also putting in place a US Space Force to enforce the US's claims to some of these things. I'm going to just very quickly, I've only got a slide or two left. I was going to very quickly going to switch over to this Vision for 2020 document, just to show you something that was produced some time ago. I'm just going to stop the share. Switch over. There. Share screen. Okay. So this is the Vision for 2020 document produced by the United States Space Command. Originally, it was part of the US Air Force, and now it's a separate force. And so you can see here that this is a document produced in February 1997. So this is 24 years ago it was produced. So this is the American military saying how they wanted to have more of a presence in space. And you can see that it's rather more like an advertising leaflet for Ming the Merciless than the American Space Force, including the Star Wars lettering down here. And it's got some rather worrying phrases in it where they talk about space power, and phrases down here: information superiority relies heavily upon space capabilities, full spectrum dominance. Clearly the American military are looking to have military dominance of space. Space trends, the challenge extends to space. So this really is a move by the American military to say, you must get us access to space, you must allow us to have surveillance, or maybe even weapons up in space. So you can see this is all a very laden sort of document, the wording used, including here a sort of space-based laser system. So last slide or two. So this is what I was saying here earlier. Space is increasingly being seen as a valuable commercial resource, not just commercial, but also military resource. And when you've got something that's up there waiting to be used, there is this sort of vacuum that industry and the military will rush in to fill. So, final slide. The Americans want to dominate the use of space, but of course not the only ones. The Russians will want to be there as well. The Chinese will want to be there as well, and so will other nations. They will all want their slice of space. There are no international laws or treaties that absolutely govern the way space works. The Outer Space Treaty is now a very old-fashioned law, 1967, long in the tooth. I can't see it being overhauled, because the problem is you try and overhaul it. There are now too many interested parties to want to do a good and fair job of overhauling it. Smaller countries are going to be left behind. India, not a small country, but in terms of their space presence, it's much smaller than the US or Russia or China. And then you've got some issues with what happens if you get some countries who don't want satellites passing over, that are going to be beaming global internet down to their citizens. China, for example, are not going to like it when they've got Starlink satellites passing overhead and potentially allowing their citizens to see the outside internet and not just the one internet that the Chinese want you to see. What about places like Iran and so on, where there are going to be problems? You could have potential for maybe someone to take a pot shot at these satellites. And then what about the case, maybe this is a bit cynical of me, just as my final parting shot, or one of my parting shots, you may have the ability to turn off these satellites over a given country. What leverage do the American government have on companies like SpaceX to say, okay, we don't approve of Iran, therefore you are going to turn off all access to the internet over Iran or over North Korea or something like that? You have the potential of digital sanctions being imposed on a country by just one company, because it's controlled by their government. So I think you can see that not only are mega constellations going to be a problem for astronomy, ground-based and space-based, they're going to be a problem for the amount of debris in space and therefore the safety of space and the sustained use of space. And they are going to be a problem legally and politically going forwards into the future. And there are potential for world tensions that may come about because of that. Okay, thank you very much.